Hello, welcome to the third lecture in the series of Pulse and Digital Circuits course. Last class we have discussed about response of low pass RC circuit for a sinusoidal input, and we have seen output wave shape is same as input wave shape for a sinusoidal input when it is applied through a low pass RC circuit, that is linear circuit. And we have seen the response, magnitude response as well as phase response. From magnitude response we have calculated the bandwidth of low pass RC circuit, that is exactly equal to upper cutoff frequency. Bandwidth of low pass RC circuit is same as upper cutoff frequency. Okay. And also phase may be changes from 0 degrees to minus 90 degrees. That means output leads input. That also we have seen. Okay. And low pass RC circuit acts as low pass filter which passes low frequencies up to a certain cutoff frequency which is known as upper cutoff frequency. Okay. So that's why it is called as low pass filter or low pass RC circuit. Both are synonymous. And now we are going to study in this lecture response of low pass RC circuit for a step input. Step input means constant voltage. Okay. So we will see it. Before going for that one, first we will see what is the importance of capacitor in RC circuit. What is the function of capacitor in RC circuit? That we will see. First, the main function of capacitor is to store energy temporarily in the form of electric field or voltage, because electric field and voltage are proportional to each other. So capacitor function is to store energy temporarily. Remember it, we are saying it temporarily. Generally we will call it as main function is to store energy in the form of electric field or voltage, but it has to be temporarily. Even if the capacitor is fully charged, after some time it gets discharged. Okay, that's why we are saying it as temporarily. So this is a function. It has to store energy temporarily in the form of electric field. That energy can be calculated with the help of formulas W. Say W is equal to energy stored by the capacitor, then it can be calculated using Q square by 2C or CV square by 2 or Q into V by 2. Q is nothing but charge stored by the capacitor, C is the capacitance value, V is voltage across capacitor. With the help of these three formulas you can calculate W, energy stored by the capacitor, where Q can be calculated. Q is charge stored by the capacitor, which is C into V, and capacitance is defined as the ability to store. Capacitance is the ability to store energy by the capacitor, and capacitance can be measured using farads. That means units of capacitance is farads, but farads is very large. That's why in general, okay, microfarad, nanofarad and picofarad are most common units for the capacitor or capacitance. Okay, these are the most commonly used units for capacitor or capacitance. Next, when a capacitor starts charging, generally we know that when capacitor it can either charge or discharge. So when a capacitor starts charging, when a current flows into capacitor, it starts charging. From that time onwards it starts charging. So when the current flows into capacitor, the capacitor starts charging and it can charge towards final value. Okay. So now we will see one example. Look at these three circuits. All are having the same source voltage along with some resistance. This resistance can be external resistor or it may be considered as source resistance of voltage source. Okay. So 10 volts with a source resistance of 1 kilo ohm. Otherwise 10 volts is applied to a resistance capacitance combination where R is equal to 1 kilo ohm. So for the same voltage you are applying 3 capacitors. So make it as C1, C2, C3. This is C1, it is C2, this is C3. 3 capacitors you applied. Now what happens whenever you are applying this voltage? Voltage stored across C1 will be equal to 10 volts because capacitor charges towards the final voltage 10 volts. As you know, capacitor stores energy in the form of voltage. So capacitor stores 10 volts and VC2 also stores 10 volts. VC3 voltage across this capacitor also after some time it will become 10 volts. Okay, but what is the difference? The difference is mainly in how much time does the capacitor takes to reach the 10 volts. How much time the capacitor is taking while reaching 10 volts. That is the basic difference. So for that one we are going to define one unit that is called as time constant. Time constant. Time constant, it is indicated with tau and units for this one are seconds. Time constant for a RC circuit is tau into R into C. Tau is equal to R into C. So time constant for a RC circuit is product of R and C elements. Resistance will be in kilo ohms, capacitance will be in farads. So multiplication of that one is resulting in seconds, tau. Capacitor, this is very important. Capacitor requires minimum of 5 time constants of time to reach the final value. So if you apply 10 volts, capacitor, if it has to reach 10 volts, you must apply that 10 volts for 5 time constants of time. Say some tau is equal to 1 second. So you must apply 5 seconds, at least 5 seconds you must apply 10 volts. Then only the capacitor can able to charge. And after that one, if you remove also, capacitor has charged the 10 volts. Okay, but minimum of 5 time constants of time is required to reach capacitor towards final value. Okay, so based on this one, we will see how much time it is taking, the minimum time to reach the 10 volts. For this capacitor C1, make it as 0.1 microfarad and capacitor 2 is 1 microfarad, capacitor 3 is 10 microfarad. We know the R value is same, but capacitance is going to be different. So 5 time constants of time, that is 5 tau. It requires minimum of 5 tau time. First you will see tau value, okay, and later we'll go for the 5 tau. So tau is R into C. Tau means R into C1, tau 1, 5 tau 1. R into C1 means 0.1 milliseconds. And for this one, tau 2 is R into C2, which is 1 millisecond. For tau 3, it is 10 milliseconds. That is R into C3, which is 10 milliseconds. And to reach final value, it requires minimum 5 time constants of time. That means 5 times of this tau. So it requires minimum of 5.5 milliseconds and 5 tau 2 is equal to 5 milliseconds. 5 tau 3 is equal to 50 milliseconds. So first capacitor C1, if it has to reach the 10 volts, it requires only 0.5 milliseconds. If you apply that voltage source of 10 volts for 0.5 milliseconds, that itself is sufficient so that capacitor C1 reaches final value. If you are coming for the second capacitor C2, the same 10 volts, if it has to reach, it requires 5 milliseconds. For C3, it is taking 50 milliseconds. That means capacitor C1 charges very fast, capacitor C2 moderate, capacitor C3 is very slow. So charging of a capacitor is inversely proportional to time constant. Charging of a capacitor is inversely proportional to time constant. If the time constant is small, charging is faster. If the time constant is large, charging is slow. So charging of a capacitor is totally depending on time constant. Okay, and if the time constant is small, capacitor charges rapidly. If the time constant is larger, capacitor charges slowly. That is very important. Okay, capacitor charges slowly when time constant is large. Otherwise, capacitor charges rapidly, that means fastly, when the time constant is small. Okay, that's what we have seen from this example. Okay. So till now we have seen capacitor charges. Okay, capacitor charges means capacitor stores energy in the form of either voltage or electric field. So we are talking about voltage in terms of, and how it is charging also we have seen. The same concept is applied for discharging also. Not only charging, discharging also. So capacitor requires minimum of 5 time constants of time to reach final value. Final value may be positive voltage or negative voltage. If it is positive voltage, we call it as charging. If it is negative voltage, we call it as discharging. That's all. That is the only difference. So either the capacitor, if it is charging also, it takes 5 time constants of time. If it has to discharge also, it takes same amount of time. That is 5 time constants of time for discharging completely. Already capacitor has charged 10 volts, for example. If it has to discharge, you are not applying any external voltage. Now it has to start discharge. The discharging is completely done. That is, it will get 0 volts after minimum of 5 time constants of time. So charging and discharging is entirely depends on time constant of the circuit, and minimum it requires 5 time constants of time. Next, look at the another example. For this one, we kept the capacitance value is same. R value is same. R value is same. Capacitance is also same. So tau is same for this one. That means tau is 1 millisecond. Tau is 1 millisecond. Circuit time constant is same. And now I am going to change the applied voltage. Once I will apply only 1 volt. Next I will apply 10 volts. Next third case I will apply the 100 volts. Okay. How much time does the capacitor takes in 3 cases when different voltages are applied? Okay, when 1 volt is applied, to reach that 1 volt, how much time the capacitor takes? If you apply 10 volts, the capacitor, how much time does it take to reach 10 volts? Similarly for 100 volts. Okay. In all the cases, it requires only 5 time constants of time. That means 5 milliseconds, 5 milliseconds, 5 milliseconds. So capacitor doesn't depend on the applied voltage. Capacitor doesn't depend on applied voltage. Capacitor directly depends on time constant of the circuit itself. Okay. So first important conclusion. Okay. Capacitor starts charging when current flows into it. Current flows into it. Second one, capacitor charging depends only on time constant of the circuit. Time constant of the circuit. It doesn't depend on applied voltage. Whatever the applied voltage, it takes the same amount of time. So irrespective of applied voltage, capacitor charges towards final value in 5 time constants. If you check the voltage across capacitor after 5 time constants, it will be always equal to final value. And third one, okay, we know that one, if you applied the voltage for more than 5 time constants, capacitor reaches the final value. If you apply less than 5 time constants, what can be the voltage across capacitor? Definitely it is less than 10 volts or less than 1 volt or less than 100 volts in all these three cases. Okay. So what can be that voltage? If you want to calculate capacitor voltage at any instant of time, if the time is less than 5 time constants, then we need a formula. That formula is this one: voltage across capacitor at any instant of time. That can be calculated using this equation, and this equation is not only valid for time less than 5 tau, it is also valid for time greater than 5 tau also. At any instant of time, the time may be greater than 5 tau or less than 5 tau or equal to 5 tau. So at any instant of time, voltage across capacitor can be calculated by using this formula. This is very important. Okay. So entire pulse and digital circuits is depending on this formula. In every class we are going to talk about this formula, so you must remember this one, and we will see what is meant by each and every letter in this one. What is meant by VF, what is meant by VI, what is T, what is TI, and RC. RC is nothing but tau, that you know. So this is the RC circuit given, R and C, and Vs is the voltage applied. Voltage across capacitor at any instant of time is defined as Vc of t is equal to Vf minus Vi into e power minus of t minus Ti by Rc. Vf means voltage across capacitor at t is equal to infinity. That means if the voltage is applied for infinite amount of time, how much voltage is stored by the capacitor? That is, capacitor stores that value. Generally capacitor requires only 5 time constants, but if you apply more than that time also, what happens? Capacitor charges that value. Okay, that we are saying ideally. Final means if you apply it for infinite amount of time, what happens to capacitor? Capacitor stores the applied voltage. That's all. So Vf means voltage across capacitor at t is equal to infinity. Ti is the time at which input voltage, that is source voltage, is applied. At what time source voltage is applied, that is treated as Ti, initial time. Ti means initial time, the time at which source voltage is applied. Whether Vs is applied across t is equal to 0 or t is equal to 5 at t is equal to 10. If the Vs is applied at t is equal to 10 milliseconds, then Ti will become 10. If the Vs is applied across 100 milliseconds, then Ti becomes 100 milliseconds. That is the time at which source voltage is applied. Vi, voltage across capacitor at t is equal to Ti. At that point, what is the voltage across capacitor? Voltage across capacitor at Ti is treated as Vi in this equation, and Rc is the time constant of the given circuit. Okay. From this equation, okay, we can get two important conclusions. Remember this one. First conclusion is, whenever source voltage is constant, voltage across capacitor increases exponentially with time constant Rc. Not only increases or decreases. That is capacitor charges, we can call it as. Okay, capacitor charges either increases or decreases. If you apply positive voltage, it looks like increasing. If you apply negative voltage, it looks like decreasing. But both are going to be charging only. Okay, charging exponentially towards that positive voltage or towards that negative voltage with time constant. So when the source voltage Vs is kept constant, that means whenever you are applying a constant voltage for a capacitor starts charging towards that value exponentially with time constant tau. Tau is nothing but Rc. Second one, capacitor requires minimum 5 time constants of time to reach the final value. Capacitor requires minimum 5 time constants of time to reach the final value. These two we have seen already. Okay. Next we will go for one simple problem. Let us assume you are applying 10 volt step for a RC circuit given where R is equal to 1 kilo ohm, C is 1 microfarad. We are going to calculate Vc of t at t is equal to 1 tau, 2 tau, 5 tau and 0.5 milliseconds, 2.4 milliseconds. Okay. So for this one, We know Vc of t, voltage across capacitor at any instant of time. So we know this equation. Voltage across capacitor at any instant of time, Vc of t. Okay. So first you need to find out what is the value of Vf, what is the value of Ti, what is the value of Vi, and what is the value of Rc. So if you know these values, if you are able to identify these values, that is sufficient. You can calculate voltage across capacitor at any instant of time. Vf is the final voltage. If you apply the same voltage for infinite amount of time, how much voltage is going to be stored by the capacitor at infinity? So 10 volts if you are applying, capacitor stores 10 volts. It requires minimum 5 time constants of time. If you apply more than that one, it will be storing 10 volts definitely. So Vf is 10 volts. Ti, when Ti means initial time where you are applying input voltage, that is 10 volts when you are applying. 10 volt step is defined like this. So if it is Vs, source voltage, okay, 10 volts is defined in this way. 10 volt step signal. Step signal is always starts at 0. Okay, this is simply it is 10 into u of t. Vs is equal to 10 times of u of t. U of t starts at t is equal to 0 and it maintains 1. 1 into 10 means 10. So when you are applying the 10 volts at t is equal to 0. So this 0 is nothing but Ti. Ti is 0 now. Next Vi. Vi means initial voltage. Voltage across capacitor at t is equal to 0. At t is equal to 0 you are applying 10 volts. By that time the voltage across capacitor is 0. Because before that t is equal to 0 you have not applied any voltage. So that capacitor has not charged any voltage. Capacitor has not charged any voltage because before that t is equal to 0 you are not giving any voltage. Whenever you are not giving any voltage, capacitor doesn't store anything. So capacitor is uncharged. So at that time input you are applying as 10 volts. By that time capacitor has 0 volts. That is the voltage across capacitor at t is equal to Ti. So it is 0. And Rc, product of R into C, 1 kilo ohm into 1 microfarad, which is equal to 1 millisecond. So all the values we know now. Okay. So now the equation is turning towards Vc of t is equal to 10 into 1 minus e power minus t by 1 millisecond. This is the capacitor voltage equation at any instant of time. So first one, when t is equal to 1 tau, 1 tau and tau is equal to Rc, that means 1 millisecond. So 1 into 1 means 1 millisecond only. By that time Vc of t is equal to 10 into 1 minus e power minus 1. So it will be equal to 10 into 0.632. So which is equal to 6.32 volts. When the capacitor is allowed to charge for one time constant of time, then the voltage across capacitor is reaching 6.32 volts. From this one we can define the time constant. Okay. Time constant definition. Time constant is tau, which is Rc for this RC circuit, and for LC circuit it is different. Okay, for RL circuit it is different. Remember it. For time constant is the amount of time required for the capacitor to reach 63.2% of its final value. of its final value. Remember it, this is final value. Now 10 is multiplied with 0.632, that's why it is becoming 6.32. If you apply 5 volts, it will become 3.14. So this will be the final value. It is going to be stored by the capacitor, but this is the amount of final value, the percentage of final value, it is stored by the capacitor in one time constant. Time constant is only in the e power something. So e power minus 1. 1 minus e power minus 1 is nothing but 0.632. Okay. So time constant is the amount of time required for the capacitor to reach 63.2% of its final value. Already we know capacitor charging doesn't depend on the applied voltage. It only depends on percentage of applied voltage. Okay. 100% it reaches in 5 time constants. If you are applying only for one time constant of time, it reaches 63.2%. Similarly, if you are going for 2 time constants, t is equal to 2 tau. 2 tau means 2 milliseconds. Tau means 1 millisecond, 2 tau means 2 milliseconds. By that time, Vc of t is equal to 10 into 1 minus e power minus 2. Because t by tau, t is 2, tau is 1, 2 by 1 is 2. So this will be around 86%. So 8.6 volts you will get. E power negative, as this negative value increases, e power value is going to be decreases. So you will get more voltage. Similarly for t is equal to 5 tau. 5 tau means 5 milliseconds. So Vc of t is equal to 10 into 1 minus e power minus 5. It is almost equal to 9.94 volts. 9.94 is treated as 10. So that means capacitor charges towards final value if it is allowed to charge for 5 time constants of time. Similarly, if you want to calculate it for the 0.5 milliseconds of time at t is equal to 0.5 milliseconds, then Vc of t can be calculated as 10 into 1 minus e power. Small t should be replaced with 0.5 divided by 1. So that means 10 into e power 0.5. So that value you can calculate, okay, which is less than 8.6. Similarly, if you want to calculate it for the 2.4, replace this one with minus 2.4 divided by 1. That is e power minus 2.4 you will get. Like this you are going to calculate voltage across at any instant of time. So we can draw the output waveform in this way. Okay. So initially capacitor value is 0. Capacitor charges exponentially and it reaches final value after 5 time constants of time. After that it will be same. So this point is treated as 5 tau. And whenever it is reaching 63.2%, that will be treated as 1 tau. 63.2%, that is 6.32 volts. So this is Vs and it is Vc of t or V0 of t, voltage across capacitor. That is output voltage. We will see one more example so that you can understand the meaning of Ti and Vi. V initial and T initial. Draw the output response of low pass RC circuit with tau as 1 second. Assume the capacitor is initially charged. This is the input signal applied. For the given input signal, you are going to draw the output response of low pass RC circuit if the circuit time constant is 1 second. Assume that capacitor has not charged any value. Okay. So we are applying it to a low pass RC circuit. V0 of t, which is equal to Vc of t, and this is Vs. So from 0 to 2 milliseconds, 0 to 2 seconds, time is in seconds. During 0 to 2, Vs is 0, and 2 to 4, Vs is plus 5 volts, 4 to 6, Vs is minus 5 volts, 6 to 8, Vs is plus 10 volts. Okay, so it will be looks like if you are going through the time durations, Okay, 0 to 2, you are applying 0 volts as constant value. 2 to 4, 5 volts you are applying as a constant value. 4 to 6, minus 5 volts you are applying it as a constant value. During 6 to 8, 10 volts you are applying it as constant value. Okay, and the duration is always 2 milliseconds. 2 seconds. 2 seconds is the duration of time where you are applying some constant voltage. Either it may be plus 5, minus 5, plus 10 or something else. Okay. Remember that capacitor charges exponentially when a constant voltage is applied, and to reach that final value, that is applied constant value, it requires minimum of 5 time constants of time. 5 time constants is nothing but 5 tau. So that's it, 5 seconds. So if you apply this plus 5 for 5 seconds, then capacitor reaches that plus 5. If you apply minus 5 or plus 10 volts for minimum of 5 seconds, capacitor reaches that value. But you are applying only for 2 seconds. 2 seconds is always less than 5 seconds. So capacitor cannot reach final value. That is, applied voltage cannot be reached by the capacitor. Capacitor cannot reach applied voltage. Remember this one. So always capacitor voltage is less than the applied voltage, because you are allowing the capacitor to store for 2 seconds only, but it requires minimum 5 seconds to reach the applied voltage. Okay. So now I am going to draw the tentative waveform, that is expected waveform I will draw. Okay. Since 0 to 2, what you are applying is 0 volts. Whenever you are not applying any voltage, capacitor also cannot able to charge. So this red line represents capacitor voltage, and from this point at t is equal to 2, understand, at t is equal to 2 seconds you are applying plus 5 volts. Plus 5 volts you are applying at t is equal to 2 seconds, and now the capacitor starts charging towards plus 5. Okay, with time constant as 1 second, but this plus 5 volts is allowing only for 2 milliseconds. So capacitor cannot reach the plus 5 volts because it requires minimum 5 tau, that means 5 seconds. So it requires only, it is going through some portion, some expected value. This value you need to calculate, and when capacitor is reaching this value, again you are applying minus 5 volts as constant, that too for 2 seconds of time. So whenever you are applying a constant voltage, capacitor starts towards that voltage exponentially, but it requires minimum 5 time constants of time, but you are allowing only 2 seconds. So it also not reaching that minus 5 volts, it reaches only a part of that voltage, and again it is also exponential but with negative slope. Next, at t is equal to 6 seconds, again the input voltage changes to plus 10 volts. That plus 10 volts you are applying it constantly for 2 seconds. During that 2 seconds, capacitor charges exponentially towards that value, but it cannot reach that value as the time applied is less than the sufficient time. So it is reaching towards a value exponentially. Later, at t is equal to 8, what you are applying is 0 volts. 0 volts is applied for infinite amount of time. Once it is becoming 0, there is no change. That means 0 volts is applied for infinite amount of time. So capacitor starts charging towards 0 volts. That means discharging. It has previously some positive voltage, now it is coming down to 0 volts. That means discharging. So capacitor starts towards 0 volts, and it requires minimum 5 time constants of time. So it discharges and it becomes 0 after some time. Can you find out this point? At what time it becomes 0? Capacitor voltage becomes 0. Whether capacitor charges or discharges, it requires minimum of 5 time constants. So it requires 5 seconds of time. You applied 0 volts at 8. So after 5 seconds means 8 plus 5 is 13. So at 13 seconds, at the time, when the time reaches 13 seconds, capacitor totally discharges. After that, capacitor has a value of 0 volts. So this is tentative output waveform, and now we are going to calculate each and every point. So this is 1, 2 and 3. These 3 points if you indicate, that is enough. That completes the problem. Okay. So first case we are going with 0 to 2 seconds, later 2 to 4, 4 to 6, 6 to 8 and above 8. Case 1. And remember it, for anything, okay, we know the voltage across capacitor equation. We know the voltage across capacitor equation at any instant of time. So for this one, Vf, first, during, when the time is between 0 to 2 seconds, what is Vf, what is Ti, what is Ti and what is Vi. We know RC value is given, okay, and Vf final value, what you are applying is 0 volts. So Vf is 0, Ti is 0, Vi is 0. So from this one, Vc of T, since you are not applying any voltage, capacitor voltage is also 0 volts. No need to use the formula. Second case B, when the time is between 2 to 4 seconds. 2 to 4 seconds, what you are applying is plus 5 volts. So final value of the capacitor when it is applied for infinite amount of time is also plus 5 volts. Next, Ti, when you are applying that plus 5 volts, initial value Ti is nothing but it is the initial time at which Vs is applied. Vs, that means plus 5 volts for this case. Plus 5 volts is applying at 2 seconds. Okay, now Vi, voltage across capacitor at T is equal to Ti. At T is equal to T, voltage across capacitor is this point, that means 0 volts. Okay, now you are going to calculate Vc of T. Substitute these values. So it will become 5 into 1 minus e power, okay, minus T minus Ti, T minus 2 divided by RC divided by tau. This is the equation, and we require the voltage across capacitor at T is equal to 4. At T is equal to 4, Vc of the voltage is equal to, simply substitute that small t is equal to 4. So Vc of T is equal to 5 into 1 minus e power minus 2 by 1. T is 4, 4 minus 2 is 2, 2 by 1 is 2, e power minus 2. This will be around 86%. So 86 means 4.12 volts. 4.12, 4.32, sorry, 4.32 or 30. Okay, 4.32 volts. So this point is 4.32. Voltage across capacitor at T is equal to 4 is this much. Next, third case. For third case is nothing but when the time is between 2 to 6. Vf, applied voltage 2 to 6 means this is, sorry, 4 to 6. 4 to 6 means you are applying minus 5 volts. So final value capacitor can charge towards minus 5 if you apply it for the infinite amount of time. So Vf is minus 5 and Ti, initial time at which minus 5 is applying. At T is equal to 4, you are applying minus 5. So initial value is nothing but 4. And Vi, voltage across capacitor at T is equal to 4. At T is equal to 4, voltage across capacitor just now calculated as 4.32 volts. 4.32 volts. Next. And now Vc of T can be written as minus 5, okay, minus 5 minus of minus 5 Vi is minus 4.32 into e power minus t minus 4 divided by tau. T minus 4 divided by tau. So from this one you can calculate at the end of this duration at t is equal to 2, Vc at t is equal to 6 is equal to okay minus 5 minus into minus, it will become plus 9.42 into e power minus 2. So this will be around minus 3.14 something you will get. The value is not exact, you can calculate it using calculator. And next case D, the duration between 6 to 8. Duration between 6 to 8, applied voltage is 10 volts. So we are going to calculate V final, T initial and V initial. Okay, V final is 10 volts, capacitor charges towards that one, and Ti when 10 volts is applying is at t is equal to 6 seconds and Vi is minus 3.14. At the end of t is equal to 6, just before this case we calculate as 3.14 volts. Now Vc of t can be calculated as Vc of t can be calculated as minus Vf plus 10 minus 10 minus of minus 3.14 into e power minus t minus 6 divided by tau. So Vc of t is equal to 10 okay, minus 6.86 into e power minus of t minus 6. Tau is 1. Okay, so at t is equal to 8 seconds, at t is equal to 8 seconds, 8 milliseconds, that means Vc at t is equal to 8 can be written as 10 minus 6.86 into e power minus 2. 8 minus 6, t substituted with 8, 8 minus 6 is 2, 2 by 1 is 2, e power minus 2. So it will be around 8.14 volts. Okay, and we know how to calculate E case because t greater than 8. For t greater than 8, Vs is equal to 0 volts and we are applying it for the infinite amount of time. Vc of t reaches 0 volts when time greater than 13 seconds. Okay, no need to calculate below that one. If it is asked, then again you can use the same equation, you can put that amount of time asked. Okay, so now you can draw these values. This is means 8.14, it is minus 3.14 like this. This is how you are going to calculate voltage across capacitor at any instant of time. If you know initial time, if you know initial value, that means voltage across capacitor at initial time, if you know final value and the time constant of the circuit. It is very easy to solve the problems. Okay. Today we will stop and next class we will discuss about response of LPRC circuit for a step input. Thank you.